All right, chemistry students, so let's look at chapter 18. We are talking about equilibrium, and I'm going to walk through the interactive reader a little bit and use that to help you study for the upcoming test. And we're going to use the interactive reader and also add on a few other things as well. So just stick with me. We're looking at chapter 18, and we're talking about equilibrium. Okay? Um, we really have been talking mostly about equations that maybe go in one direction, but now we're going to be talking about equations that go forward and reverse. They go in both directions. And we've looked at reactions that have gone only one direction. For example, a strong base or a strong acid, like a strong acid HCl, completely dissociates, meaning there is no HCl left in the solution. It is all going to be ions. So this is only a one direction. Whereas a weak acid, like this one, this is hydrofluoric acid, this will go one direction, but it'll also go the other direction. So these ions are formed, but also those ions turn back into the original compound. So that's a weak acid. It only partially dissociates. So that would be the difference between those two. We're looking at reversible reactions now in this chapter. So a chemical reaction in which the products can react to form reactants, it goes both directions, that is a reversible reaction, and that is denoted by the double arrow. Okay? Every reversible reaction is going to reach a point which we call equilibrium. Equilibrium does not mean that the reactants are equal in concentration to the products. That's not what it means. They may be close, but that's not what it means when we talk about chemical equilibrium. It means that the reaction rates, how fast the reactants are turning into products, that rate is the same as the rate at which the products are turning back into the reactants. And that happens after a certain amount of time. It's going to be reached eventually. Okay? So we say that it is in a state of equilibrium. It actually is a dynamic state of equilibrium because the reaction never stops. It continues and continues and continues, but your concentrations, the concentrations of the reactants in the product are not going to change because you've reached a point where the forward direction and the reverse direction are happening at the same rate. So as soon as a reactant turns into a product, you're probably having a product turning right back into a reactant, and the concentrations on both sides are not going to change significantly. Okay? Dynamic. You have to know that it's dynamic. It doesn't mean the reaction stops. Okay. When you balance your equation, we've been balancing equations for a long, long time. You know that in this case, the N, the M, the X, and the Y are representing your coefficients in your balanced equation. A and B are your reactants, C and D are your products. Okay? So all this is saying here is that as the reaction proceeds over time, the forward reaction, the rate, it's changing very quickly at first, just like the reverse reaction is changing very quickly also, but then those rates basically are going to reach a constant, and that constant is going to be the same. This is reaction rate now. This is not concentration. So the two reaction rates are going to actually become the same value, and they're going to become a constant. So this forward rate and the reverse rate equal to each other, and they become a constant value, meaning they're not changing anymore. That's when you've reached equilibrium. Okay? Okay. In addition, let's look at this value that we've been calling the equilibrium constant. So it's very, very helpful when we look at a balanced equation, and let's again just write this one here. Our N and M, X, and Y are representing the coefficients in your balanced equation. A and B are your reactants, whatever those compounds are, whatever the species are. C and D are representing your products. it is very, very helpful to come up with a single value to give you some information about the reversible reaction and its equilibrium position. Here's what I mean. If you take the concentration of your products and you divide them by the concentration of your reactants, you will create what is called the equilibrium constant, and it is going to be represented by K. So for any reversible reaction, we can calculate a ratio, it's a mathematical ratio, by taking products, concentration of products, over concentration of reactants. More specifically, here's how you find it. You take the concentration of all of your products. That's what the brackets mean. The bracket means concentration. Okay? So the concentration of C times the concentration of D over the concentration of A times the concentration of B. So if you've got more than one product, you multiply the concentrations. If you've got more than one reactant, you multiply the concentrations of the reactants in the denominator. In addition, if you have a coefficient in your balanced equation, if x is 2, for example, these coefficients become the exponents right there, and there, and there, and there in your equilibrium constant expression. Because in some cases, a species may be doubled or tripled, and so we have to take that into account in your equilibrium constant expression. So this is how you find the K value, the equilibrium constant expression for any reversible reaction. It is always products over reactants. It is the concentration of the products multiplied together, and the coefficients become the exponents, over the concentrations of the reactants multiplied together, and again, their coefficients become exponents. Okay? Now, why this is helpful is if we know this ratio is products over reactants, then if this value, if this K value that we find, by the way, this is at equilibrium, always calculated at equilibrium. You don't calculate this K value until you've reached equilibrium. Once you've reached equilibrium, then you take those concentrations and you plug them in. If this calculated K value right here is really small, it could even be, you know, the factor of like 10 to the negative 3, 10 to the negative 7, 10 to the negative something. Really small, less than 1, really. If it's less than 1, that means you've got what? You've got lots of reactants and not very many products. So if this value is very small, that means the numerator is small, the denominator is big. So that means you've got lots of reactants, very little product. If it's close to 1, that means you've got about equal amounts of the two. And if this is bigger than 1, if it's a large value, when I say bigger than 1, or I say large, that's what I mean, that means you've got fewer reactants and lots of products. So it's very helpful, this number right away. So you look at the number, you kind of know the relative concentrations between products and reactants once you've reached equilibrium. Okay? And this constant K is going to always be that value for that particular reversible reaction. It doesn't matter what the concentrations are that you start with. It doesn't matter if you start initially. I'm not talking about equilibrium. If you start with a lot of products, only products, and it reacts, turning into some reactants, back and forth, reversible reaction, you will reach that K value, whatever the K value is. Doesn't matter what your beginning concentrations are. That reversible reaction at a particular temperature will always reach its K value. If you change the temperature, then you get a different K value for that reversible reaction, and we'll look at that. Okay? So the equilibrium constant provides a measure which tells us what is favored. Are the products favored, or are the reactants favored at equilibrium? As I said, if K is small, then you've got lots of reactants, and we say it's reactant favored. If K is big, that means that we've got lots of products, and we say it is product favored at equilibrium. Okay? So here's a simple example. Here's a reversible reaction, and you are told that this would be at equilibrium, saying Here's the concentration of the nitrogen at equilibrium. Here's the concentration of the oxygen at equilibrium. Here's the concentration of the nitrogen oxide at equilibrium. And they're asking us to find the K. Well, you just plug into your formula. You first have to write the formula. Here's your product, and your coefficient is a 2. Notice that concentration is going to be squared. Here are your two reactants. Neither of them, well, they have a coefficient of 1. So you just plug in the concentrations that are given here, and don't forget to square that one. Concentration here, concentration there, and evaluate that, that value there. That would be your K value. Notice how small it is. Very small, which means at equilibrium, it is reactant favored. Now, one other very, very important thing. You never, never, never put solids or pure liquids into the equilibrium constant expression. Never put solids, never put liquids. So if you see S or L next to a compound, a species in your reaction, that particular species is not going to go into your K expression. Just omit it. Don't even put it in. That's because this K expression is working with things whose concentrations change. A solid has a fixed density. Its concentration is not going to change. A pure liquid like water, its concentration is not going to change. So you don't put pure solids, don't put pure liquids ever into the K expression. Only aqueous solutions and gases. Okay, let's look at what happens if you, once you've reached equilibrium, what happens if you mess with the reversible reaction? That is called applying a stress. There are different stresses that we can apply to a system after it's reached equilibrium. Once it has attained equilibrium, those amounts, the concentrations of the reactants and the products will stay the same unless you start to mess with it. If you start to mess with it, then it's going to shift to try to get back to an equilibrium position. So we're looking at chemical equilibrium. If we do make changes in the pressure, the concentration, or temperature, those three can affect the equilibrium position. They may not change the K value. So pressure, concentration, the K value stays the same. But temperature will change the K value. Only temperature, changes the K value. These other two, even if you change pressure and concentration, the K value will still stay the same. It'll get back to that same K value. Okay? This whole idea is called Le Chatelier's principle. The idea that if you change something once it's reached equilibrium, the reaction will shift forward or reverse to get back to a K value. Either the original K value, or if you change temperature, a new K value, but it's always going to want to get back to equilibrium. Okay? So let's look at these three really quickly here. If you change pressure, so if you have a reversible reaction, and let's say that's happening inside of a container, and then you change the volume of that container, which affects the pressure, or maybe it's in a syringe or something, or it has a piston that you push down, or it's in an expandable container, and you change that pressure, this is going to shift in order to try to relieve some of that stress that you are adding. It's really simple. Here's what you need to do. You need to figure out the total number of moles on the reactant side, which would in this case be 1, and 3 for a total of 4 moles of reactants. On the product side, you have a total of 2. Okay? So imagine if you were to add pressure, you increase the pressure, things are getting squished together. What is this going to try to do to relieve some of that pressure? It's going to shift to the side that has fewer particles. Fewer particles, then you got fewer particles ramming into each other, and you're going to relieve some of that added pressure that you just put on the system. So if you, in this case, you have to find out which side has the fewer number of total particles. In this case, it's the product side that has fewer total particles. If you increase the pressure, it will always shift to the side that has fewer particles. Okay? So you're going to try to restore equilibrium. Equilibrium is restored by moving to the side that will help relieve that stress from the pressure. So if you add pressure, if pressure goes up, the reaction is going to shift to less moles. Okay? If pressure goes down, then it's going to shift to the side that has more moles. Sorry, this is not working very well, but not writing very well. Okay? Okay, let's look at changing concentration. Let's use the same reaction. If you change concentration, again, the reaction is going to shift to try to either replace what you've taken away, replace some of it, or it's going to use up some of what you've added. It is always going to want to get back to that K value. So remember, K value is products over reactants. So if you change one of the products, you're changing the numerator, which means it needs to replace some of those products. It needs to get that number back up, and it does it by lowering also the reactants so that it can get back to that same ratio. So our reaction was N2H2, okay? And I think this was 2 and 3? Oh, 3 and 2, okay. So if you, let's say this has reached equilibrium, if you now take away some of the nitrogen, if nitrogen concentration goes down, you're able to remove some nitrogen some way. That means you just upset this K value. The K value here would be NH3, the concentration of NH3 squared, over the concentration of the N2 times the concentration of the H2 cubed. If you take away some of this N, you're lowering the denominator. So this has to replace some of that partially, not all of what you took out, but it's going to replace some of it. So it's going to shift to the left. We say it shifts left. It needs to make more of what you took away, and then this also will go down a little bit, and this will go up a little bit. So the reaction is going to lower the NH3, it's going to increase the H2, and it's going to increase the N2 so that it can get back to that same K value where it was before. If I was to increase something, let's say I added more hydrogen, so I increase hydrogen, okay? If I increase hydrogen, that means that I've upset this K value again. I just increased the denominator. It wants to get back to that same K value. I made the denominator too big, so it needs to shift this way, use up some of that H and use up some of the N2, so the N2 will go down, H2 will go down, and H3 will go up a little bit in order to get back to the same ratio. You won't have the same concentrations, but the concentrations, when you plug them in, will give you the same K value that it was before. Okay, and now let's talk about temperature. Temperature is the only one that will change the K value, okay? So the K value will change when you have changed the temperature. Here's what it does. The K value will always adjust, or let me say it this way, the temperature will always cause the reaction to shift in the endothermic direction. okay? It needs to, if the temperature increases, you want to use up some of that heat energy, and you do that by kicking in the endothermic direction. Okay? The endothermic direction will always use up energy. How do you determine the endothermic direction? Well, you have to be told where the heat is in the reaction. So if heat is found over here as a product, then the endothermic direction is reverse. If heat is found over here as a reactant, sorry, those are reactants, okay, and products there. Then if heat is over on this side, then when you increase the temperature and add heat, it's got to use up that heat by going that direction. So it always wants to react away from the heat. If you increase temperature, listen, if you increase temperature, if you add heat, it's going to react to use up that heat, whatever side the heat is on. It may be a value in kilojoules or something like that. Then it's going to use up that heat by going in the direction away from that heat. That's how you'll always know. And it will make a new K value. So in this case here, if I add heat here, this product is going to go down, this reactant is going to go up, and you will have a K value that is going to be smaller because you just increased the reactants but decreased the products. If it goes the other way, you're going to decrease the reactants and increase the products, and your K will get bigger. So in this case, the K value is going to get smaller. In the case down here, the K value will get bigger. Okay? All right. So that kind of wraps up the first couple sections. And I need to add a few other things, and I'm going to do that in the next video. So I'm going to pause here, and then there'll be a second part to this.